So hello, welcome to the last class. This is the last video I'm making for you guys. Yes, we have the final, and yes, I'll be in Zoom during the final, but I'm not going to be recording it, or I'm not really going to be doing anything. So this is it. You sat through way too many videos / Zoom lectures of me talking, so congratulations, you deserve something for it, which I guess that something is college credit, because you took a class, that's what you get. I really didn't think through that sentence before finishing it. So, general idea, this is the last class. This is the end. I'm not holding any more office hours. I'm not doing anything else. I'm done. Your final, you have a homework due Sunday the 13th. Don't forget that. And you have your final at 5:30 p.m. on the 14th. Definitely don't forget that. If you have any questions between now and then, you can always email me. I will respond to the emails. If you really want to meet with me on Zoom, I might be able to. I'm not quite sure what. Well, I don't go anywhere these days. There's a pandemic, so I mean, it's not like I won't be around. Um, but if you need to talk to me, let me know and we can work something out. But other than that, I want to do practice problems for chapter 31. And so I'm going to jump in. Now, chapter 31 has a lot more, doesn't have many equations. The equations from the chapter are what I put here. And honestly, two of these can be simplified. Because this E of n equation, every single one of these terms is a constant. And so that's the same as just negative 13.6 EV 1 over n squared. And this R of n equation, all of these are a constant. So that's the same as positive negative 0.0, oh, I'm blanking on the number, 529 nanometers n squared. And so really when you add that in, they're all very simple. So let's get into these problems though. The first one says, what is the energy of a photon that, when absorbed by a hydrogen atom, could cause an electronic transition from n equals 2 to n equals 5? Well, here's the idea. Each energy state has an amount of energy. Each energy state's energy is given by that huge-ass equation I wrote up there, which I simplified to negative 13.6 EV over n squared. And, I want to do that. Sorry, I just had a note for myself. And so I could then go and say, I can then just say that the energy required to go from one state to the other is just going to be the difference of the two energies. If I wanted the energy from going from 2 to 5, I'm just going to say, what's the energy at 2? The energy at 2 being negative 13.6 EV over 2 squared, or 4. I did it all in one step. Awesome. What's the energy at 5? The energy at 5 is just going to be negative 13.6 EV over 5 squared, or 25. And therefore, the energy needed would just be the change in energy. It'll just be negative 13.6 EV over 25 minus negative 13.6 EV over 4. Or if I wanted to factor, negative 13.6 EV 1 over 25 minus 1 over 4. And I can just do that math. It's 2.86 EV. It also asks what's the difference between 4 and 6. If you want to do distance between 4 and 6, I'm just going to use the same logic and just say it's going to be negative 13.6 EV. And I'll make these 4 and 6 respectively. Well, 6 squared is 36. 4 squared is 16. And get that. I could convert these to joules. They'd be 4.68 times 10 to the negative 19 and 7.56 times 10 to the negative 20, respectively. But nowhere did it say you had to convert it to joules. So why bother? I could have also done it using the Rydberg constant and figured out the wavelength, and from wavelength gone to energy. That would have worked also, but that just seems more complicated. Although even if I did decide to do that, that equation would just be saying 1 over lambda equals OH 1 over m squared minus 1 over n squared, and how energy is hc over lambda, which means the energy is hc, Rydberg's constant, 1 over m squared minus 1 over n squared. And if you were to go through and do that, you'd find that hc lambda, or hcrh, ends up being positive 13.6 eV. The negative sign comes because these switched the orders, that it would be flipped. So, would have been the same. Let's go into the second problem. Consider a large number of hydrogen atoms with electrons all initially in the n equals 4 state. How many different wavelengths would be absorbed in this emission spectrum of these atoms? Now, if I do something like this, I'll tell you what the various emission lines are. Okay, sorry, that's not what I'm saying. I misread that. So we're saying a large number of hydrogen atoms initially in n equals 4. So if we look at the states, we have 1, 2, 3, 4, with them getting closer together. And it says how many emission lines are possible. This is kind of a more complicated question than I think I'd really want to give on an exam because it takes a lot more thought. But let's think about it. The quick answer is 3. From 4 to 1, from 4 to 2, and from 4 to 3. But here's the thing. If electrons relax from 4 to 3, I don't want that color. If they relax from 4 to 3, that means they're in 3. They can then do from 3 to 2 and from 3 to 1. And if they relax from 4 to 2, they can then go from 2 to 1. And so you have 1, 2, 3, 4, 5, 6 different possible wavelengths. That if something's in the first state, you would see 6 different lines. And if you look at the atomic spectrum, yeah, 6 lines will be in it. It then says, what is the longest wavelength that can be absorbed? Well, okay. If I look at the energies here, the energies, this is going to be the highest energy. But that's not what I want. Energy and wavelength are inversely proportional. As I just said last one, energy equals hc over lambda. And so the longest wavelength, when lambda is a maximum, that's going to be when E is a minimum. If I want to find where E is a minimum, it's going to be the smallest gap. So it's going to be one of the times it only moves one step, from 4 to 3 or 3 to 2 or 2 to 1. But something else to keep in mind of. The radius is given as a constant times n squared. And something I talked about in class is these get closer as they go out. I kind of drew this here where this gap is bigger than that's smaller and that's smaller. But really to scale, it should be more like here's 1, here's 2, here's 3, here's 4. That the further out you get, the closer the energy levels get at an exponential level. And so the smallest gap will be the smallest energy, will be the longest wavelength. And the smallest gap would be when we go from 3 to 4. And they say, what is that wavelength? Now, I could either find that wavelength by finding the energy using the same logic we just did. Or, because I gave the Rydberg constant, I can go straight to 1 over lambda equals the Rydberg constant, 1 over m squared minus 1 over n squared. Well, m is where you end up, and n is where you started. So 1 over lambda equals the Rydberg constant over 1 over 3 squared minus 1 over 4 squared. Once again, that's why I would have been off by a negative sign when I was doing this one over here, is because this m and n is swapped from the order I did these in. And so I say that 1 over lambda equals 1.097 times 10. It's 10. I can't read that. That is like, that number is like kind of messed up. I think it's 10 to the 7th. No, it's negative 2, I think. I don't know why that's messed up though. Let me go somewhere else. It's the 7th. That's not why Okay, 10 to the 7th. Oh, I know what I'm thinking. I'm thinking a different constant. That's on me. Times 10 to the 7th. I was working in nanometers, which I'm used to seeing it in. Inverse meters, 1 over 9 minus 1 over 16. Which is why I was thinking 2, so I was thinking nanometers. And I can do that math. And that is 5.33 times 10 to the 5th inverse meters. That's 1 over lambda, so therefore lambda is just 1 divided by that number. 1.88 times 10 to the negative 6 meters. And there we go. Now that wouldn't be visible. That is 188, let me think. That would be infrared. That's part of the Pashan series. Actually, yeah, relaxing from 4 to 3. That's part of the Pashan series. PASCHEN. But that's the wavelength. Now, when it comes to exam, because these are pretty straightforward, this has a good chance of showing up. It didn't show up last time. But if this does show up, I mean, it's, yeah, I kind of just plug and chug. Any questions here?
Nope, all good.
Okay. See what this next one is. Hydrogen atom is in its fourth excited state, n equals 5, because the first state is the ground state. Using the Bohr theory of the atom, calculate the radius. Okay. Well, the radius, I got the equation, I circled it up there. Rn equals n squared, h bar squared, me, ke, e squared. And I gave all the constants. But I'm not going to bother plugging those all in. I'm just going to say Rn is a whole bunch of constants times n squared. And that whole bunch of constants work out to be 0.053 nanometers. And so if I want to know n equals 5, it would just be 0.053 nanometers times 25, which is 1.32 nanometers. B is probably what is the energy level? Yep, B, the energy in this state. The energy, as we keep saying, is negative 13.6 EV over n squared. Well, once again, I could do it in terms of the constants. It is me ke squared e to the fourth over 2h bar squared. But screw that noise. It's why bother plugging those in if you don't have to. The next one takes a little bit more thought. And the next one says, what's the velocity of the electron? Now that equation, if you note, I don't have anywhere up there. But we did cover it in the notes. We derived the velocity of the electron. And in the notes, when I was going through the process, where I got the velocity of the electron, all came off. So I'm trying to decide if I want to bother deriving it again. Where it came from is that F equals ma, that the force on the electron is Ke Q1 Q2 over R squared. And that'll be the acceleration, but since it's moving in a circle, it will be mv squared over R. And we said Q would be the charged electron and charge the proton, respectively. And a whole bunch of derivation occurred. This could give me an equation for V, but then I also plugged in some other thing. Well, I guess I might as well just derive it. Instead of deriving it, I'm going to say the equation I got to the notes eventually was N H bar over MER. You could also, if I go this one, I'm going to have things with E's in them instead. I'm not doing that one mostly because, I don't know, this is the one I wrote down first. Check the notes on it. You'll find all these derivations. Now, h bar is just h over 2 pi. So that's the same as this. And so it'll be 5 times h, 6.626 times 10 to negative 34th joules seconds over 2 pi. The mass of an electron is 911 times 10 to the negative 31. And all is going to be the value of all we found, 1.32 nanometers, 1.32 times 10 to negative 9 meters. And you get 4.38 times 10 to the 5th meters per second. As I said, that equation is not one I put up here for the things you should know. It's probably not a bad one to have in mind. It's possible I put something on with it, but it's not as likely. And since I said, so I have something opening. Here we go. It just showing where it came from. It's just, it was right here that I solved for V. Oh, that's what it was. That was from saying the momentum one. That equation came from the de Broglie wavelength. That's where that equation came from. Okay.
Okay.
Next was actually simpler but more annoying at the same time. There's the other thing I could possibly do. I'm actually gonna do all 5 today because they're quick. On the exam, I might also ask something with quantum states. And so this practice problem says, what's the when the principal quantum number is n equals 3, what's our quantum states? So we're saying n equals 3. Well, there are 4 quantum numbers, n, l, m of l, and m of s. M of s is always 1/2 or -1/2. That's the easiest one. L can be everything from n minus 1 to 0. And M of L can be anything from from negative L to L. And so I can say what quantum states. I'll just go through and work out everything possible. I'll say if n equals 3, that's set. L can be n minus 1 to 0. So L can be 2, 1, or 0. Now starting at the bottom, M of L goes from negative L to L. So M of L can only be 0. Here, it can be negative L to L. It can be -1, 0, or 1. I went too high in this. And for 2, it can be -2, -1, 0, 1, or 2. Makes sense so far? And so I can just list all these. 3, 2, -2, 1/2. 3, 2, -2, -1/2. 3, 2, -1, 1/2. 3, 2, -1, -1/2. 3, 2, 0, 1/2. 3, 2, 0, -1/2. 3, 2, 1, 1/2. 3, 2, 1, -1/2. 3, 2, 2, 1/2. 3, 2, 2, -1/2. 3, 1, -1, 1/2, and so on. This is me being lazy and not feeling like writing them out.
That is a biatch.
Yep, kind of is.
I almost don't want to do that one more than I want to do the RL circuits.
If I'm gonna have you write one out, it won't be this complicated. Plus, you have to do this problem. You can't skip this one. It's one of the ones you have to do.
Oof.
Oh,
But I won't make you write out that many. If you look at last semester's exam, I think I gave you the L value also. And 5. 5 is a little more chemistry based. That I would probably like to do in the exam, but the second part of this one, because it doesn't say this, it doesn't say A and B, but there's really 2 parts, is something I might have you more do. It says, what's the electron configuration of phosphorus? And for the electrons in outermost unfilled subband, list all possible quantum numbers. So, if I want to find the electron, the configuration, the electron configuration to go the photon, I'm going to need this chart because that's the order I fill these things in. And I say I start with 1s2, 2 electrons. You know, I want to see if I can do something. See if this stays up. Then I go to 2s2. That's 2 more electrons. Next is 2p. 2p can hold 6 electrons. So I'm at 10. After 2p is 3s. This can hold 2 electrons. After 3s, and I'm just following these arrows, after 3s is 3p. 3p can hold 6 electrons. Well, I'm at 18. That's higher than I wanted to get. And before I added that, I was at 12. So 3s2, this was 4s. So if I'm at 12, wait, no. 3p, I lost track of where I was. 1s2, 2p, 3s, 3p. Did I skip 4s? 2, 2, 6, 2. Oh no, I'm on 3p. Okay. Yeah, I went out of order. 3s. So I don't know what I did here. So I'm going to start over. 1s2, 2s2, 2p6, 3s2. After 3s is 3p. What was I thinking? 2, 2, 6, 2. Sorry. And I was already saying it was 6. I just wrote the wrong thing. I think I was just writing not what I said. And so since I want to hit 15 and I'm at 12, I'm just going to only put 3 electrons though. And I'm going to put 3 electrons because that is going to add up to 15. The 2 plus 2 plus 6 plus 2 plus 3. I sound like I'm doing the movie Clue. 1 plus 2 plus 1 plus 1. So that's the configuration. Now it says, for the electrons in that shell, what is all possible quantum numbers? And this is more likely for me to do because it's not as ugly. This is 3p3. 3p3 means n equals 3, that's the 3, and p. What p means is anytime L equals 1. Now M of L still has the same rules of negative L to L. And M of S still has the same rules of negative 1/2 and 1/2. But now I don't have nearly as many this time because it's going to be 3, 1, and this could be negative 1, 0, and 1. This could be 1/2 and negative 1/2. And so it'll be 3, 1, oops, I missed my commas. 3, 1, negative 1, 1/2. 3, 1, negative 1, negative 1/2. 3, 1, 0, 1/2. 3, 1, 0, negative 1/2. 3, 1, 1, 1/2. 3, 1, 1, negative 1/2. And really all of these should have been in parentheses. If I do something with this, I'll probably go close to this, where it's only like a few of them. I won't give as many as that last problem.
All right, that's nicer.
Yeah. Any questions? My phone is exploding. I need to mute it. Okay. So these problems really shouldn't be too crazy. They get kind of ugly if you don't do the shortcuts that I wrote up here. The ones I have kind of written in bad handwriting up here. If you don't do the shortcuts, they're kind of a mess. But other than that, you just kind of go for it. Okay? We're going to stop there. Thank you for taking Physics 2. Hopefully you enjoyed it. At this point, really, as I said, this class becomes chemistry. If you want to go further with physics, you're really going to need calc-based to go any further. If that's something you plan on doing, good luck with it. I will say students who have taken this class and gone on to other schools to continue, there have been a few. If you get stuck in any other physics classes, you can always email me, even when I'm no longer your professor. I've been tutoring people at SUNY Oneonta who went to Delhi before. But I hope you enjoyed. It was an interesting semester, and good luck with whatever you do with it. Bye.